In this PowerPoint, we're talking about the force of friction.
So in our first example, it says a force of 40 newtons accelerates a 5.0 kilogram block from rest at 6.0 meters per second squared along a horizontal surface. What is the force of friction acting on the block? Okay, so the first thing we do, we see some forces are involved here, so we have to use Newton's second law in order to find our force of friction. Later on, we're going to be able to come up with an equation for the force of friction, but whenever you don't have a specific equation for a force, you always have to go back to Newton's second law. And before you complete Newton's second law, you got to do a free body diagram. So we identify all the forces that are acting on this block. Well, we have this 40 Newton force that is pushing the object forward, so that's our force 1. We also have a force of friction that's acting on it, so that's identified here. It has a mass, and we know that it's going to have weight, so that weight is identified here as the force of gravity. And then since it's on a horizontal surface, that horizontal surface applies a normal force upward. So we know that those are all the forces that are acting. Now the purpose of a free body diagram is to get our forces organized so that when we complete Newton's second law, we're looking specifically in one direction or another. Now when we say net force equals mass times acceleration, we're looking specifically for the force of friction, and we know that's in the x direction. So we don't just put all of our forces in for the net force, we put only the forces that are in the x direction into this equation, and then separately we can do the forces in the y direction into Newton's second law. Since we're looking specifically for the net force, we're going to look in the x direction. So if you look at this, we see force 1 and force of friction are both in the x direction. Now force 1 is in the positive direction, it's to the right, and then force of friction is in the negative direction, it's to the left. So when we put in our forces for net force, we put force 1 is going to be positive, and then force of friction is going to be negative. So technically it's force 1 plus a negative force of friction, but we can just write that as force 1 minus force of friction due to their directions in the x direction. And that's going to be equal to mass times acceleration. Now we know the acceleration is going to be horizontally, so there's no acceleration vertically. So we can go ahead and plug in the information we know. First of all, we know that the force 1 that's applied forward is going to be 40 newtons. We know that the mass is going to be 5 kilograms as indicated in the problem here, and then the acceleration is 6 meters per second squared. So in order to find the force of friction, it's the only unknown, and we go ahead and take 5 times 6, and that gives us 30. So 40 minus the force of friction is going to be 30, and 40 minus what number would be equal to 30, and that's going to be 10. So force of friction is 40 minus 30, and that gives us 10 newtons for our force of friction. And now keep in mind that friction usually opposes the direction that it's sliding. So if we're pushing the object forward and it's sliding forward, then that means that the force of friction is going to be opposing, and it's going to be in the opposite direction. For this example, it says a 7.5 kilogram block is sliding along a horizontal surface with only friction acting on it at negative 12 newtons. Its initial velocity is 4.8 meters per second, so we need to know two things. We need to figure out what the acceleration is, and we need to figure out how long it takes until it stops. Okay, so to find the acceleration, there are several ways to find acceleration. From Unit 1 and Unit 2, we used the kinematic equations like velocity equals acceleration times time plus the initial velocity. But in this unit, we have Newton's second law, where net force equals mass times acceleration. And since in the problem it looks like forces are given to us, then that's exactly what we're going to use. But before we start with Newton's second law, we first have to start with a free body diagram. So we know that these are the forces that are going to be applied. Now notice normal force upward because it's along a horizontal surface, so that surface is applying an upward force. The object has mass, which means it has weight that's pulling downward, and then we have this force of friction acting on it at negative 12 newtons. Now notice it says only the force of friction is acting on it, and what that means is there's no forward force being applied in order to push it forward. Essentially, as it's sliding, friction's the only thing that's acting on it to cause it to stop. So when we're trying to find the acceleration's in the x direction. So we go to Newton's second law, and net force is going to be equal to mass times acceleration. And since we're looking in the x direction, we're looking in the horizontal direction, there's only one force that's there, and that's going to be the force of friction. So that's what we're going to put in for the net force for this side. Only the forces that are in the x direction. So force of friction is going to be equal to mass times acceleration. Now when we put in the force of friction, we know it's going to be negative 12. Because it's in the left direction, and the x direction is going to be negative 12 for that. And then we get our mass in here, which is 7.5, and then our acceleration. We go ahead and divide both sides by 7.5, and we find that our acceleration is negative 1.6 meters per second squared. So that gets our acceleration. That gets the first part of finding that. Now how long does it take to stop? So how much time does it take? Well, if you notice, we have the acceleration, we have the initial velocity of 4.8 meters per second. The final velocity is going to be 0 because it's going to stop. Now, given that we have the acceleration, the initial velocity, the final velocity, and we're looking for time, then we're going to use this equation right here. Final velocity equals initial velocity plus acceleration times time. Then we go ahead and plug in our numbers, and we find that the time is going to be 3 seconds. Now, this equation comes specifically from the first and second unit. So if you haven't realized yet, physics builds on top of each other. So we talked about kinematic equations, and then that leads into forces and motion, and all that's going to build on top. So we're going to use those equations in the future as we keep going through the unit.
Now, the force of friction is caused by the microscopic roughness of two surfaces. Now, we have to take into account both surfaces. We can't just talk about the roughness of one surface, because sandpaper on a block of wood or sandpaper on another piece of sandpaper are going to have very different amounts of friction. So the surfaces look smooth, but when you get on the microscopic scale, they're actually not. Now, if you notice with these forces of friction, when these two surfaces are in contact with each other, you have a force that's being acted on in each one. Now, if you think of force as a vector, and this vector is at an angle, then there's a horizontal component and a vertical component. The horizontal component is what gives you friction. The vertical component is what gives you the normal force. And then there's a ratio between these two components depending on the roughness of the surface. So what attributes to the amount of friction between two surfaces? Well, friction is proportional to the amount of normal force that's being applied and the roughness of the surfaces, which is called the coefficients of friction. Now, the mu sub s and the mu sub k, that has to do with static friction and kinetic friction. Static friction is when an object is not sliding. Now, force of friction, friction will be applied that will balance in order to prevent something from sliding. So let's say the maximum amount of static friction that can be applied is 20 newtons. If I push on it with 10 newtons, it's not going to push back with 20 newtons with the maximum amount. It's going to push back with 10. So it's just going to do enough to balance. Now, if I push on it with 15, it pushes back with 15. If I push on it with 19, it pushes back with 19, all the way up to 20. Now, if I push on it with 20.01, that's more than the maximum, and it'll start to slide, and that's when we move over to kinetic friction. Now, after I get it to start to slide, the object is going to continue sliding regardless of how much force I'm applying to it until it stops again, or until it just keeps going. But the amount of static friction is constant. So if the amount of static friction is 15 newtons and I'm pushing on it with 20 newtons, it's going to push back with 15. If I'm pushing on it with 10 newtons, it's going to push back with 15 the entire time. Now, because force is a vector, then there's a proportion between the force of friction and the normal force. If you remember from the previous slide, the force of friction, that was the horizontal component of the force between the two surfaces, and the normal force was the perpendicular force between the two surfaces. The roughness of the surface, the mu of s and the mu of k, coefficients of friction, that's the constant proportionality that tells you the proportion between friction and normal force, and that simply has to do with the roughness of the surface. So the maximum amount of static friction is always, always, always greater than or equal to kinetic friction. You'll never have kinetic friction greater than static friction. It's just not possible. The reason for that is if I get something to move that overcomes static friction, that means it starts to slide. But if I don't overcome kinetic friction, then that means, well, it's going to slow down. So how can you start sliding and then slow down if you're already not moving? So kinetic friction will never ever be greater than static friction. Now, how will this help if you're driving on wet ground or ice? Well, when our cars are driving, the wheels are actually turning, and when they're turning, they're not sliding. Now, static friction and kinetic friction, the terms static and kinetic, usually static is a word that means not moving, and kinetic is a word that means moving. In this example, it's not really moving and not moving that we're looking at. Static is going to mean not sliding, and kinetic is going to mean sliding. So what type of friction do we use while driving? Well, we're not sliding our wheels. Our wheels are gripping the road, so they are using static friction. And since static friction is always greater than kinetic friction, or greater than or equal to, then that's going to mean that the amount of static friction that's being applied, as long as your wheels aren't sliding, you're going to get more traction than you would if it was kinetic. Now, in this example, this chart kind of shows what happens if I apply a force on an object that has friction. Then this is going to be the amount of friction that's going to be applied back to me. So let's say this maximum amount right here is 20 newtons. If I apply 10 newtons, force of friction is going to apply 10 newtons back. I apply 15 newtons, force of friction is going to apply 15 newtons back. I apply 20 newtons, force of friction is going to apply 20 newtons. I do just a little bit more than 20 newtons, now all of a sudden we have a force of static friction. It's going to start sliding. So if I apply more and more and more force, the amount of static friction, the amount of kinetic friction is going to be constant the entire time. So let's suppose this is 15. If I apply 20 newtons of force, then force of friction is going to apply 15. I apply 30 newtons of force of friction is going to be 15 the entire time. So while it's not sliding, friction applies as much force as needed in order to balance whatever force that I'm applying, but after it starts sliding, the force is going to be constant. Now this chart looks at some of the coefficients of friction. You can see that we have static friction in this column, we got kinetic friction in this column. In the static friction column, you see that the static friction coefficient is greater than the coefficient of kinetic friction. Now that means the amount of friction as compared to the normal force is going to be greater for static friction than kinetic friction. And that's important when we're using our cars and driving on the road. You want to use your static friction. You want your wheels to start turning. You don't want them to be sliding because you get less friction out of it. Now if you see with wet concrete, the coefficient of static friction goes down by about 30%. And then if you're sliding on wet concrete, it goes down even more. You have half as much friction as you would have if you were driving with static friction on a dry amount of concrete. So this is why we have anti-lock braking systems in our car. It's also why your driving instructor tells you have to pump your brakes when you're sliding, because when you're sliding you have a lot less friction and you're not going to be able to stop as quickly. If you let your wheels turn, you take your foot off that brake and then hit the brake again, then you're going to be using your static friction. You're allowing your wheels to turn and not slide. So that way you're more able to stop. If you ever slam on your brakes, it actually takes a lot longer to stop than it would if you pump your brakes and allow to use that static friction.
In this example, it says a force of 40 newtons accelerates a 5 kilogram block from rest at 6 meters per second squared along a horizontal surface. Now, I'm not sure if you realize this, but we've actually done this problem before. This is the problem where we found the force of friction. So to give you a little bit of a background on this, just a reminder that this was our free body diagram when we were talking about the force of friction, finding the force of friction, and we found that the force of friction was 10 newtons. You should be able to go back in your notes and see this problem that we did earlier, or earlier in this PowerPoint if you want to go back in this video. So essentially what we're doing now, though, it says what is the coefficient of kinetic friction? Well, now we have a specific equation to find the force of friction, and there's only one equation that has a coefficient of friction in it. And the only equation we have for coefficient of kinetic friction is this one right here, where force of friction equals coefficient of kinetic friction times normal force. Well, we already found the force of friction before, but now we need to find the normal force. In order to find the normal force, you see that the normal force is in the in the y direction. It's in the vertical direction. So that means we need to do Newton's second law again in the vertical direction in order to determine the normal force. So looking at the vertical direction, there are only two forces here. So we don't include the force of friction. We don't include force 1 because we're just looking in the vertical direction. Normal force is in the positive vertical direction. Force of gravity is in the negative vertical direction. So those are going to be the two forces that we include in our net force. Now we know that there's going to be no acceleration in the vertical direction because it is accelerating horizontally at 6 meters per second squared. So that we know the net force in the y direction is going to be 0 because all the acceleration is horizontal. So normal force, which is positive, plus a negative force of gravity or minus force of gravity is going to be equal to 0. Now we have an equation for force of gravity. Force of gravity is going to be equal to mass times the acceleration due to gravity. So that's going to be our 5 times 9.8, which gives us 49 newtons. And since we go ahead and solve this equation, we bring the force of gravity to the other side, we find that the two forces are equal to each other, then the normal force is going to be equal to 49 newtons also. So now we're going to take this 10 newtons of force of friction, plug that in, the 49 newtons of normal force, and plug that in, and then we're going to isolate our coefficient of friction. So we divide both sides by 49, and we find that our coefficient of friction is going to be 10 divided by 49, which equals 0.204. Notice the coefficient of friction doesn't have a negative sign because it doesn't have a direction. It also doesn't have any units. So keep that in mind, that a coefficient is a ratio between two measurements that are the same unit. So this is in newtons, 10 newtons, and then 49 newtons. The newtons are going to cancel, and that leaves us with no units.